Hi everyone, welcome to HK Cybersec YouTube channel. So we have a special guest today whose name is Blake Jacobs, aka Joyd, with the Twitter handle. Hi Blake, how are you? Hi Jacobs.
You're not too bad. Yourself, I'm very good.
Yeah, I'm doing good. Thank you for asking. All right, so can you introduce about yourself quickly?
Yeah, sure. So my name is Blake. I go by the handle Zoid. And yeah, I've been interested in like cybersecurity, information security since the age of 16. I've got a kind of a weird story. So I started off just making like short films, and then I moved on to like cartoons, and I got really fixated on making cartoons. And then I stumbled across Linux, and then I started making Bash scripts, and then I found a great interest in programming. So from there onwards, I started getting more into like security, and that's when I researched on YouTube how to crack a wireless password. And at the time, it was WEP that was used extensively, like everywhere. And started cracking my wireless network password, and then I learned like it was very vulnerable. So um, yeah, so then I moved on to like cracking wireless networks to like using Metasploit and learning how to like exploit computers. And back then, I'm talking about like 6 years ago, even more. They had this Windows vulnerability. It was an SMB vulnerability, and my sister's computer was running the vulnerable operating system. It had an outdated, I think it was a Windows XP Service Pack 2 machine. And I scanned the network and I found out that her computer was vulnerable, and I exploited it. And I'm like, that's when I kind of had that like moment where, wow, doing this sort of stuff is pretty powerful. And then it was very exhilarating. So then I moved on to like doing some pretty like bad stuff. It wasn't that bad. Like I cracked wireless network passwords in my neighborhood and sold them and that sort of stuff. But then that was my kind of my grey hat day. Then I transitioned from away from that bad stuff to learning like web security and helping protect companies and with their security, making sure the security is up to date and all that sort of stuff. Um, so I did. Then I went moved to web security and did that for a while, and then I found like bug bounties and how like you could get paid hacking websites. Um, I started off like just I don't know finding cross-site scripting vulnerabilities, just a very low-hanging fruit stuff, as we all do. We all start somewhere, um, and then just reaching out to like other hackers that are high up there, asking them questions. And I kind of figured out that staying away from the crowd is key. And in order to do that, you got to try and avoid doing what everyone else is doing. So then I kind of did some research. I talked to a few hacking friends, and that's when I stumbled across Path Normalization. And Path Normalization was one of those types of bug classes that not many people were looking for. And I kind of gained a big interest in that, did some research. And then once I found my first Path Normalization misconfiguration, it just got me fixated on it because I knew that like a lot of them weren't duplicates. And that's what this presentation will be about. I'll teach you how to fingerprint Path Normalization, how to exploit it, and we'll go over other interesting stuff about it as well.
Awesome.
Hello, welcome to Path Normalization Misconfigurations, breaking path normalization for fun and profit. My name is Blake. I love to program in various languages including Golang, Rust, Python, PHP, lots. I work as a developer for Pentester Lab. In my spare time, I like to make and play games, as well as participate in bug bounties. I also have a startup called cyberlix, which is an external attack surface management platform for bug bounty hunters. We'll talk a bit about that later. But what's on the agenda? We're going to be talking about what a reverse proxy is, what is path normalization, and different ways we can fingerprint proxies, how we can break path normalization, discover an internal applications, and what is the impact for these types of attacks, and the takeaways as well. So what is a reverse proxy? A reverse proxy is a server that accepts a request from a client, either a client being in a browser, for instance, forwards the request to another one of many other servers. So in this picture down the bottom here, this diagram, this is pretty much how a reverse proxy works. It's a complete opposite of a proxy server or forward proxy server. So in this diagram, we have the servers. It could be, for instance, Google. Google might have a public facing, like a public server, which might host the Google's main domain, you know, google.com, the main root domain, and then they might have a bunch of other backend servers or other backend applications that are hosted on servers that are kind of, you know, protected through a reverse proxy. So that comes to the next stage where we have the reverse proxy, and then we've got the internet, and then we've got us, the end users. That's us. That's our, we are navigating to Google using our browser on the internet. It gets sent through a reverse proxy, and it gets upstream to the recording server. So if we type in google.com, it will go through the reverse proxy. A bunch of filtering and normalization will happen, and then it will look for that host header. And then whatever that host header is, it gets upstream to that server that has that web application hosted on it. And if we're living in Australia, generally we'll load the Australian Google, because we're getting upstream to an Australian-based server from, you know, that has Google hosted on it or whatever. But say we've got Google has a back-end application that's kind of isn't allowed to have external access to it. Like, you know, it might be a back-end admin API, or it could be, I don't know, a staff lookup or a portal of some sort. If we try to access that directly from the browser, it's going to go through the reverse proxy, a bunch of filtering and normalization will occur, and then it will pretty much present us with a 403, or it may redirect us because we haven't got permissions to access that web application that's on that internal server. So that's pretty much a reverse proxy. It can be used as a security mechanism. It can be used to speed up a web application as well. There's many use cases, including load balancing. It's very handy. So it's very useful to have implemented. So what is path normalization? So path normalization typically involves manipulating a string that identifies a path or a file to assure that it's a valid path on that target operating system. And so developers will often use path normalization techniques as a security mechanism to avoid sensitive data from being accessed. Reverse proxies such as Nginx have filters that act in a similar fashion to path normalization to avoid backend services, micro APIs, etc. from being directly accessed. In other words, to block external access to internal applications. So what are some different ways we can fingerprint proxies? Figure out what sort of proxy we're dealing with. So one thing we could do is look at the response headers, such as caching headers or server headers. Sometimes the server header might leak the server that the web application is hosted on. For instance, it might leak Nginx or Apache, things like that. We can use Wapalizer. Now, you can use the Wapalizer browser plugin, but I've had a lot better results with the headless Chrome. I'll just get out of this slide quickly and I'll show you a tool that I use that's written in Rust. I just got to find it first. This one here. So this one here is a Wapalizer written in Rust, but it's a headless Chrome. It's a headless browsing one as well. So I found using this one here, you can either use the tool, the standalone executable, or you can use it, you know, as a library as well. When you want to write or incorporate Wapalizer in your Rust tool, you can use the library as well. But this one here uses Chromium-based browsing to detect technologies used by an application, and I find that the browser extension picks up way less stuff than this actual Wapalizer written in Rust. It's really useful. I use this tool with my tooling all the time. I use this library within my tools. It's really useful. Let's go back into the slide. Whoops. So the last one, there's probably many other techniques we could use, but these are the three most common ones I use. So the last one is to perform a path-based attack, such as path traversal, and looking at the page contents for changes and things like that. So the technique, the first one we're just going to cover is the traversing paths. This is the most used one I use all the time. And this involves traversing the directory. So for instance, traversing the routes. So for instance, if we have a route like /etsy.clientlibs, we might do a path traversal back a couple of directories and look for different status codes, like a 400 bad request, and we'll talk about what those mean later on. But this is typically what you want to do if you're looking for if you want to fingerprint what the proxies that are being used. And what we'll do is we'll leave that one there, but we'll go. There's another actual GitHub repository which will actually be really useful when you're learning this type of attack, and it's called Weird Proxies. And there's actually a list of servers or proxies that have different ways of fingerprinting. So, for instance, if we click on Apache, we want to look at how path normalization is dealt with in Apache. You know, it tells you the basics of Apache, like some of the case sensitive for verbs. So get is not the same as a capital get. You know, a double slash is treated as a directory. Doesn't allow hash fragments and percentages and percentage 00 in the path. So there's a lot of different things that talk about Apache, and I use this to help learn about how I can break path normalization, because I know that for instance, Apache doesn't allow a percentage 2f, so I would just not try that type of payload, which would be like a dot percentage 2f. So I won't even try that, because it always is treated as a 404. It also tells you a bit about fingerprinting. So for the Apache server, this is coming from that the server header, and you know the value is Apache. You can fingerprint an Apache server by looking at the 400 error. So this is what the request will look like if it's Apache, and the 403 error will look like this. And you can go over some of the other servers, for instance, in Nginx. It tells you a bit about that as well, and how you can fingerprint that as well. So breaking path normalization, this is when we get into the really cool stuff. So breaking path normalization usually involves using path-based attacks, such as a path traversal payloads that allow the URI that follow the URI request for comments to find inconsistencies within reverse proxies and the filtering in place by looking out for changes in the response headers and status codes. And this can be achieved by traversing out of the public web route into the internal web route. Okay, so before we go over an actual demo, I want to talk a bit about the request for comments for URL. So if we go to this website here, datatracker.ietf.org, and we navigate to the request for comments section for a uniform resource identifier. These are the kind of the standards or the rules that make a valid URI. It's like the syntax for a programming language. What actually makes a valid URI? And if we scroll down, it talks about lots of different things like considerations, security, merge part. Like there's lots of stuff about URLs. And one of the sections that talks, like even look at this, parsing a URI reference with regular expressions. So it talks about using regular expressions to parse a URI. It talks about malicious construction, you know, reliability and consistencies. But there is actually a section down here, we do a quick search on normalization. Right here. So this talks about normalization. So simple string comparison, syntax-based normalization. If we locate this part here, for instance, this is the syntax-based normalization. So it will also talk about normalization, path normalization, talks about the kind of like a very minimal algorithm, like a very basic algorithm to normalize paths. Let's see if I can find that for you guys. there was a section here that talked about how to implement path normalization. I guess maybe you guys can have a look at that when this slide finishes. But what I'm basically trying to lead up to is there's actually this part here. So this talks about, this actually gives us some basic payloads we can try out when we're trying to detect, path normalization misconfigurations. So we can try out some of these techniques, like we've got this semicolon x equals 1. These are different types of // attacks we can try. And yeah, look at this. This is one I've looked at, and I picked up a few payloads that I didn't even knew existed, and I used it and find some really cool stuff. And here it is. So this is the basic algorithm to or pseudocode to implement path normalization. So actually no, this is the basic pseudocode to parse UI components. Sorry, maybe I got that bit incorrect. I think there was an algorithm here somewhere. Yeah, removing dot segments, and this is the pseudocode to do basic path normalization. So it tells you how you can implement path normalization. And a lot of like programming languages like Golang, they normalize paths by default. So they would implement something like this. Alrighty. So for a demo, I'm not going to show you a vulnerable target, but I'm actually going to show you kind of an example of how we would test for path normalization misconfiguration. So if we load up, for instance, Yahoo. If we load up for Yahoo, we could load up Burp. We could spider a bit to collect a list of paths. We could even use Go Spider, which is a tool made by I think Jesse on GitHub. You could spider. You could do a bunch of recon, but what I like to start off doing is inspecting the network traffic. So what I'll do is I'll reload the page, and I would look for paths here. For instance, look at this one here. Let's load this one up, and we'll load that up. And you just start basically traversing. Obviously, it's way easier in Burp. And again, I'm very sorry I couldn't actually show you this on a live target. I can't really find many labs out there. There's one on Pentester Lab that you could try out, but I don't have permission to show you that one just because it's a pro exercise. So what you would typically do is you'd start trying out a bunch of path normalization, a bunch of path traversals. You can see this one's a 44 not found. We tried going back a bit more. Nothing interesting. And then what I would typically do is if I get all the same response when traversing with a specific payload, this one being a semicolon /, I try a different payload until I find a payload that works and retrieve something different. So look at this. This one says edge not found. So this one's returning a different response. Let's go back one more. We still get the same response, but it is a little bit different. So maybe we want to try using the similar payload. So we might try a %2e, %2e, %f. Nope, that didn't work. And again, if we form these traversals in like Burp or using using Burp or curl path as is. Curl path as is, it doesn't normalize the paths. Burp doesn't normalize paths by default, but browsers sometimes do. So for instance, a payload like just a normal standard .. It's not the browser's going to normalize that, and it's just going to return the web root. So you have to use the .. in like a program like Burp or using curl path as is. So you typically, I might try a semicolon A equals A, right? And that's actually found on the request for comments as well. So I might try again the same one until I find something that's similar to, until you find like maybe a 400 bad request, or you might start finding something from weird proxies. For instance, you might find this status here, 400 bad requests, and you might get this like response. It might be a 400 bad request, and then when we get a response like this, if you haven't memorized all the responses for the different servers, but say we get a response like this and you're not sure what that response means, you could go to this weird proxies Git repository, a GitHub repository, and you could look at it and go, okay, this looks exactly the same response. It must be in Nginx. And sometimes the server header will leak that, sometimes it won't. So sometimes you need to use your brain, your pattern recognition, to determine what the server is by looking at the response. For instance, say it returned this response right here. We will then go, we'll go to this website, and we'll go, boom, it's Apache. And then we'll we'll look at traversing, or looking at part traversal payloads based on these rules here. So, for instance, if it was Apache, we wouldn't do a %2f because that isn't allowed in Apache servers. It just will always treat it as a 404. So this is like kind of the general guideline we can go by if we get a response like a 400. And then what we'll do is when we get this 400, we will go forward one directory. If we get a 404, that's when we'll do the content discovery to find internal routes. And that would be our next slide, discovering internal applications. So this would be the next stage we would need to perform. We would need to perform a directory brute force using tools like FF or dir search to find hidden internal routes to access. Now, when we do get valid results, say we get like a /manager or a /admin route that just pops up and gives us a 200 with a response size greater than 0, right? Much larger than 0. You don't want to have like a small response size of like 1 because there might just be a little bit of data there. So upon discovery, we need to check if the route is accessible in the web root. We'll talk about what that means. But if it is in the web root, then it's just a basic misconfiguration, meaning that the file or route is just unprotected. So let's have a look at what that actually means. So say we do like a traversal on Yahoo. Let's go back to Yahoo, for instance, and say we found like say we did a traversal on API/v1, right? We did a traversal and we got a 404 right there, and we did a directory brute force, and we found a backend, like a route that was like /admin, right? Just a very basic example. Like I'm just making it up. I'm just trying to get my point across. I'm trying to give you the knowledge, give you the methods to use. So say we did a directory brute force and we found /admin, right? What you would do is you would copy that from dir search or FF and you would try it in the web root, meaning that right here. And if that returns some like 404 or 403, then that's good. That's good. And say we, when we did directory brute force, it was found here and it was like a 200 with a response size greater than 0, then we know that that's a valid result. It's cool. We've broken path normalization. We've accessed an internal route. And then we'd locate, we'd navigate to it. And if this like spits out a whole heap of JSON, we're like, I don't know, like add all the clients' users or all their clients' users or like emails or passwords. Kind of like what ZLZ found on Starbucks, which I will talk about that a bit later. Then what we'll do is we will try and, find if we can escalate it a bit more, or we might report it. But if it only spits out like, a default installation of Tomcat Manager, and we couldn't access the admin, the manager /HTML, the dashboard, we wouldn't report that because yes, it is a misconfiguration. Yes, we accessed the Tomcat Manager, and it wasn't just an unprotected route. Then we can't really do much. So that's what we'll talk about a bit later. Is the impact that comes with these types of attack vectors. So, and I've already gone over that demo, really. I've already talked about it, but the demo was going to be about content discovery and brute forcing and finding internal routes, but we already covered that one. So here's the section of what would the impact be. So the impact can be quite varied. So it can vary from low to critical, but you will often find these types of attacks result in P1s, because the reason is you're accessing internal applications that are not supposed to be accessed by the public. Some applications that are internal maybe just default installations or API routes which have nothing sensitive at all. But in most cases, they may contain actual administrative panels in Unix APIs, Tomcat instances, admin APIs with both read and write permissions, portals and dashboards, and loads more interesting stuff that may lead to a critical or a P1. So before we go over the takeaways, I quickly want to show you some other presentations. I will get Hema. I'm sorry if I haven't pronounced your name correctly, but I'll get Hema to provide these slides and all the information in the description of this YouTube video. But some of the slides, one of them being Orange's slide, breaking parser logic. He goes over some really cool techniques to break path normalization. He goes really in depth on some of the implementations and some of the code, some of the rules, filters, and he also goes over how to exploit them. He goes over like a visual way of how Windows treats a UNC and how Linux treats a URL. So he goes over really in depth on some of these attack vectors, even a polyglot as well. Hacking Starbucks by Sam Curry. He has a really good presentation on his blog, samcurry.net. He also provides a presentation attacking secondary contexts in web applications, which I highly recommend having a look at. He's got excellent experience and knowledge in these types of attack vectors. And there's also Zero Nights. This is another type of, this is another slide on reverse proxies and inconsistencies worth having a look at. So back to the slide, we're going to have a look at some takeaways. Now, a key takeaway is this bug class has not got much attention, and it's not that popular defined, like iDoors once was. I encourage you to at least incorporate this attack vector into your bug bounty methodology, because you may find you will get less duplicates and you will stay away from the crowd greatly. You'll feel so great when you find a bug, when you find one of these, because you'll kind of come to the realization that holy crap, there's no duplicates. And that's what I kind of was like when I first found my my first path normalization misconfiguration. I was like, holy crap, why am I getting dupes? You do get some duplicates, but I found most of them were through Adobe Experience Manager misconfigurations, like accessing the content repository development environment. A lot of them were kind of duplicates, but that's because there's nuclei, there's lots of articles about it, so therefore more duplicates. But if you try and find path normalization misconfigurations that are different than AEM, then you might find that you get no duplicates at all. So I really do hope you enjoyed this quick presentation on path normalization, and don't forget to pre-enroll to cyberlix. For those that don't know what cyberlix is, cyberlix is basically an external attack surface management platform aimed for bug bounty hunters, and we're going to provide tons of tutorials on path normalization, along with a complete attack surface management platform that will help you with your recon, reporting, and exploitation. You can pre-enroll at https://cyberlix.io. Thank you very much for watching. Until next time, have a great morning, great night, and bye.